If we talk about generation rate, then it actually depends upon the shape of the semiconductor and can vary with space coordinates and time. For reference, we have taken a regular cuboidal block of semiconductor and we will assume that the initial recombination rate and generation rate is GR1 and RR1 respectively. And since the semiconductor is in equilibrium, then generation rate will be equal to recombination rate. Generation rate depends upon excitation of electrons to conduction band, which further depends on photon bombardment. If the photons incident on its surface increases, then the generation rate also increases. But the generation rate increases on the surface only. For understanding it, let us assume that we are having a photon emitting device such that we are deliberately exposing one surface of cuboidal semiconductor with continuous and uniform number of photons striking on its surface from t is equal to 0 up to infinity. Initially, there will be a non-equilibrium condition, but we will not take that condition into our consideration. We will assume that after some time t, the equilibrium has been attained so that the semiconductor is in dynamic equilibrium condition. After exposing left surface of the semiconductor to photon bombardment, then the generation rate will be highest at this surface. Let us assume that at x is equal to 0, which is the leftmost point of the semiconductor, the generation rate will be approximately equal to GR2. Since we have taken the equilibrium condition, then the generation rate will be equal to recombination rate, and these particular values of recombination and the generation rate will be greater than the initial value of generation rate and recombination rate. However, as we move towards right of the semiconductor, more and more number of photons will already get absorbed, decreasing the number of photons which are still available for electron excitation. Take any point such that the generation rate at this point is GR3, which is again greater than initial generation rate of the semiconductor before applying the photon emitting device. And if we assume that the length of the semiconductor x is very long, then at the extreme right end of the semiconductor, the generation rate is nearly equal to its initial value. Now, if we try to draw a rough plot, then it will come out to be like this. Here, the blue dashed line represents the value of generation rate before applying the photon emitting device, and you can see from the graph also that at the extreme right end, the generation rate is nearly equal to its initial value. But remember that we have taken x to be very long. So you can see that the generation rate is actually dependent upon position coordinates relative to semiconductor, which has highest generation rate at its surface and will keep on decreasing as we go deeper into the semiconductor. Similarly, if you assume that the semiconductor is of irregular shape like this, then due to its more surface area, more surface excitation will take place when exposed to photon bombardment, which increases the generation rate. When we talk about an isolated semiconductor such that there are no external factors like battery or optical devices like laser, then we take generation rate to be uniform in the semiconductor even if there are minor differences in the value of generation rate at the surface and deep within the semiconductor. It is good to know that the generation rate depends upon the shape of the semiconductor. However, if the shape and size of the semiconductor are fixed, then the generation rate depends upon the temperature. So, we can write generation rate is actually a function of temperature. Unlike generation rate, recombination rate depends upon the temperature as well as concentration of free electrons and holes. We can write recombination rate is directly proportional to concentration of free electrons. Similarly, recombination rate is directly proportional to concentration of holes, and by introducing a proportionality constant alpha, we can write recombination rate is equal to alpha into free electron concentration into hole concentration. Here, alpha is actually a function of temperature and is sometimes referred as recombination rate proportionality constant. This formula for recombination rate is very important as many questions can be framed from it.